Greetings once again and welcome to another SETMind edition. In this edition, we are going to be looking at a very interesting combination of two loads. The first load is made up of two motors and the second load is made up of two furnaces. So furnaces are heating devices. You can look them up on the internet. So you can read the question here for your attention, and I'm going to be focusing on the question. So question 2, which is our first question, reads, for the loads in scenario A, which is above, calculate the apparent power for the two motors. So let's go to the next page and focus on question 2. So let's have a look at what is given, which will assist us to be able to easily answer question 2. So we are told that the first load, which is the motor, which is what we are looking for, we're looking for the apparent power for the two motors. The first load is made up of two motors rated at 300 kilowatt. So I need you to remember, when you are given the kilowatts for a motor, it is usually the output power. With an efficiency of 95%, having a power factor of 0.8 lagging. So let's go and note down what are we given here. So if you have a look, what we are given here is the output power. So we have the power out of the motor, which is 300 kilowatt. So remember, what is usually rated, it is what the motor will give you on the output. Okay? And this is the power out for the motor. And what we are also given is the efficiency of the motor. And the efficiency is given as 95%. And what we are also given is our power factor. And our power factor is 0.8. Okay. And now we can work around this and see what we can find. So the easiest thing to do is, remember, the motor is rated 300, but it has an efficiency of 95%, meaning the power that comes in is not necessarily the power that comes out. So we need to remember the formula, which is that our efficiency is always given by our power out over our power in. So what is the power that is coming out versus the power that comes in? And if you look carefully, the power which we want is the power that we are drawing, or the power that is coming in, which is P in. So if you observe carefully, P in will therefore be given by P out divided by our efficiency, which means the power which our motor is drawing will be our 300 kilowatt divided by 0.9, which is 95%. And you should be able to see that the power out will be, or the power in will be 315.789 kilowatt. And there's one thing which I need to bring to your attention, which is that our motor, obviously, whenever we see kilowatt, maybe from your courses, you should know that what you are dealing with is active power. And active power is also known as, to others, as real power. So this is the power that will get the job done, okay? But when you look at kW, yeah, that is what you should think of. So now that we have our power in, which is going to be what we use, we should remember that we have two motors. So which means we need to double this power. So the power required by our two motors will be 2 times our power in. So which means we'll have 2 times our 315.789. So the power which is demanded which is required by our motors, will be 631.579 kilowatt. So this is going to be the power required by our motors. Now we need to find the apparent power, and remember we're given a power factor of 0.8. And there's something I want to remind you of, which is the power triangle. So let's quickly draw it here. So what I need you to remember about our power triangle is that we'll have theta, and then vertically up we'll always have Q, which is our reactive power. P is our real power or active power, and then we'll have S as our apparent power. So let's quickly make notes of these. Now with all of this in mind, let's go to the next page and start finding our apparent power. So if you observe carefully, we already have our PM, which is our real power. So I'll make it M, then this is also for the motor, okay? So now if you look at our triangle, remember this triangle here, for anyone who might have forgotten, this is what is called our power triangle, okay? So if you observe our power triangle, you should be able to see that if we do the trig ratio PM divided by SM, you will see that P over S, that will give us cos of theta, of which this is just our power factor. So remember, our power factor is also always given by cos of theta. So whenever you have cos of theta there, cos of that angle, that is the same as our power factor. So this means I have all what I need to be able to determine what is SM, of which SM is our apparent power, which is what we are looking for the first question, the apparent power for the two motors. So let's go ahead. Our PM here, we have found it is 631.579 divided by our apparent power for the motor, and this will be equal to 0.8. So we can now easily find our SM, which if you look carefully will simply be 631.579, and this will be divided by 0.8. So the answer we get ends up being 789. If we round it up to one decimal place, that becomes 0.5. So which means our SM is 789.5, and remember we're working with apparent power, so it should be kVA. Okay, so now we can go and check our options, and if you look carefully, all of them have been rounded to a digit. So if you look carefully, if you round this to a digit, what we end up getting is 798. That will end up being 90. So 790 kilovars, not vars, but yeah, var. So this means that our answer will be A. So 790, that is going to be our answer. Okay. So let's go ahead now and deal with question number 3. So I hope question A makes a lot of sense. Let's go and deal with question 3 now. So question 3 requires us to calculate the overall apparent power for the two loads, meaning the motors and our furnace. And one thing I need you to note is already what we have. So we're looking at question 3. So what we already have here is our S for the motor. And our S we found as 790 kVA. But what you should note is what we are given. So if you read if you read carefully, you will see that the second load is made up of two furnaces and they are rated at 200 kA, which means we are actually given what is our apparent power. So if you look carefully, we are given that our SM or SF for the furnace, it is 200. But remember, there's two of them, which means we get 400 kVA. But however, the total apparent power cannot be summed as follows. We cannot say ST, which is the total apparent power. We can't say SM plus SF like this. This cannot happen. So our ST is supposed to be a vector sum. So it is supposed to be a vector sum, not a magnitude sum. So although we already have these, we cannot just sum them, not a magnitude sum. We cannot just sum them and then say that is the total apparent power. So I need you to remember the following about your apparent power. Your apparent power is always given by your real power plus J times your Q. So which means if we have two systems, let's say S1, which will be P1 plus J Q1, and we have another one, S2, which will be P2 plus J Q2. The total of S1 plus S2 is not the same as just only focusing on the magnitude, okay? S2, this is not the same. So when we do the total apparent power, we should add the individual parts. So we should have P1, the active power adding up. We should also have the reactive power components or demands adding up. And then our ST, when we are now looking for the magnitude, will finally be what we have here, which will be P1 plus P2 all squared, and then Q1 plus Q2 all squared. What am I saying? What I'm saying is we need to go and find the active power and the reactive power for the motors, find the active power and the reactive power for our furnaces. So let's go to the next page. So we'll start with the motor load. So let's have a look at our motor load. So for our motor load, we actually already have the active power. So PM, we already have. Let's go and have a look at our motor load, our PM. There we have it. It is that. So that is our active power for our motor, and we also have our power factor. Remember, our power factor is 0.8, which means we have cos of theta equaling 0.8, and we have already found our apparent power. So our apparent power is 790. So we had found 785.5, so we can use that one. 789.5, sorry. So our S for our motor is 789.5 kilovar. Yeah. So this is what we have. Then now what I can do is quickly use our power triangle to be able to find the active power, because the active power is what we do not have. Sorry, the reactive power. So if you observe carefully, QM is what we don't have. So let's go ahead and work on it. So let's put up our triangle like that. So we'll have theta and that, and remember we'll have PM. Sorry, it's the other way around. We'll have QM, and then PM and then we have SM. So if you look carefully, finding QM should be very easy, because what we have is we can do QM over PM. When you look at this ratio, it is just tan of theta. And theta, remember, we can easily find because cos of theta is our power factor, so which means theta is the same as the inverse cosine of our power factor. So we have everything we need to get our QM, which it is going to be PM tan of, wherever we see theta, we'll just put in cos inverse of our power factor, of which we already have.